Hey guys, welcome to the NCEA Level 3 Complex Numbers paper from 2020 worked answers. So for those of you that are joining us for this video, basically the best way to watch this video is to pause the video at the start of each question, try and work the answer by yourself, and then watch the video. I do show you guys what you need to do for achieve merit, excellence, and so on. Now this particular video is slightly different from my usual variety. This was live streamed and it's been edited out, so there might be a few little random conversations that might pop up in the middle. I do apologize about it. Try to edit as much as possible. Yeah, so without further ado, let's get started. Okay, so nice and easy. Well, never a nice thing to say at the start of the question one, but it is all right. So all we have got here is we've got two complex numbers, and we've got to actually try and figure out what the value of k is if st equals 21 minus I. So what we've got to do is we've actually got to multiply these two complex numbers here. So s and t, just kind of multiply it straight up. We're going to get 2 plus 3i multiplied by 3 plus ki. We know that the product of st equals to 21 minus I, so we can kind of say that this whole thing should equal 21 minus I. So just kind of dealing with your normal quadratic expansions there. So we've got 2 times 3, which is 6, and then 2 times ki, which is 2ki. Then we've got the bottom part of it that I've got to expand out. So I've got 3i times 3 is 9i. And then I've got 3i times ki squared, which is 3ki squared. Now all of this is equal to 21 minus I. I am going to kind of leave it as just like that. So just remember that I squared is equal to negative 1. So we're going to rewrite this whole thing as 6 plus 2ki plus 9i. What have you got? We've got 3ki squared, so this is going to end up looking like 3k times negative 1. So we've got 6 plus 2ki plus 9i minus 3k. So putting all my real values together, so my real values in this case is the 6 and minus 3k. So I can put that together, 6 minus 3k. And my imaginary values, I'm going to just take the I out and just leave the terms inside. So I'm going to get 2k plus 9i. Now all of this is equal to 21 minus I. Now interestingly enough, k ends up being on both sides. So you could just go the real part equals to real, or the imaginary part equals the imaginary part. So in other words, you could actually say 6 minus 3k is equal to 21. Or you could actually do the 2k plus 9 equals negative 1, because remember that negative I is the same thing as saying negative 1. I'm going to go with the real values, so 6 minus 3k equals 21. So I got negative 3k equals 21. Take away 6, negative 3k is 15, which then gives me k equals 15 over negative 3, or in this case, k is equal to negative 5. Now let's say you did the other way, where you did 2k plus 9 equals negative 1. Then you're going to get 2k equals negative 1 minus 9, 2k equals negative 10, and pretty much same answer. So, but that should have been a 2. Yeah, so k equals to negative 5. So grades-wise, guys, you guys have to get the right solution. Either way you do it, you have to get the right solution for an achieved. Okay, so going on to question 1b. So with 1b, what we have got here is your classic discriminant question. What we have got here is has only one solution. So this kind of has to remember from level 2 when when we're dealing with discriminants, that when we have one solution, b squared minus 4ac is equal to 0. So all we have to do is we got to work out what our a, b, and c are. So you can kind of see that a is equal to 1, b equals to 4r, and C is equal to R. So once we have that, we literally just substitute it. So we've got B squared, which is 4R squared, minus 4 times A, which is 1, times C, which is R, and all of this has to equal to 0. So then expanding 4R squared is going to be 16R squared, minus 4R is equal to 0. And you can see a nice little quadratic here with 4R as a common factor. So we can get 4R minus 1 equals to 0. So once again, we've got a quadratic, which equals to 0. So you're going to get two solutions. So 4R equals to 0, or 4R minus 1 is equal to 0. So your first solution is R is equal to 0, and your second solution is 4R equals to 1, and R is equal to a quarter. So once again, guys, you need both of these answers to get an achieved for this question. Cool. So with 1C, so what we've got with 1C is we've got a classic rearranging question with throwing a bit of square root symbols in it as well. The thing about square root symbols is that people always get kind of like muddled around with the square root symbols. Pretty much you can mess with it like where, like I've seen people do this, like I just want to show you guys, like someone, they try and kind of like do this, which is fine, all right? I mean, which is what we're gonna do. But what I mean is, like, I've seen people do this, sorry, there we go. Like when you say square, they actually take each individual element and square it. That's what I wanted to show you guys. But really, what we're gonna do is we're actually gonna do what I said originally, which is square both sides. So when we square both sides, and remember this part here, especially at the left-hand side, you do need to write 2 root x minus 5. And I would actually write that bracket again because people forget that there's a middle term, equals, and because you've got a square root with the 4x minus g and you're squaring it, the square root just disappears and you're left with just 4x minus g. Now the next thing is we've got to get rid of these brackets, right? So we've got to expand these brackets out. So first off, we've got 2 times 2, which is 4, and then root x times root x is just x, so we're going to get 4x. Minus 5 times 2 is 10, so that's going to become 10 root x. Then we have these two elements here, which is going to equal minus 10 root x plus 25, and this is now equal to 4x minus g. So far, so good. Putting them all together, so we're going to get 4x minus 20 root x plus 25 equals 4x minus g. Now, if you guys have a look at here, like, you know, your question is actually asking you to solve for x in terms of g, and we've got a root x in there. But the cool thing is we can actually get rid of this 4x and this 4x, because when you bring it to the other side, you know, this becomes 4x minus 4x, blah, blah, it becomes 0. So we're going to leave this as negative 20 root x plus 25 equals negative g. And what am I going to do next is I'm going to, well, to be honest, you can kind of do whatever you want here, because ideally you want to have x by itself. Whether we want to do it pretty, now let's do it ugly. So this ugly version is going to look like this, minus g minus 25. All I've done is taken the 25 to the right hand side. Again, looking at all those negatives, you know what, you can just get rid of the negatives, because if I divide this by negative 1, divide this by negative 1, divide this by negative 1, I'm going to end up with 20 root x equals g plus 25. Cool, still not done yet, because we want to write x by itself. So once again, we've got to square the whole thing. Now, as for the g plus 25 squared, I'm not going to bother. I'm just going to leave it as it is. In fact, I'm not even going to do this yet. Let's actually get rid of the 20 first, just to make things easy for us. So I'm going to rewrite this as square root of x equals g plus 25 divided by 20. And I guess now I can actually square both sides, because then it'll just become So much more easier, because square root of x squared is just x. And as for the right-hand side, I'm going to get g plus 25 over 20, and the whole thing is squared. So grades-wise, we are looking at a merit for this final step. Correct squaring of both sides isn't achieved. So I'm guessing you are probably looking at either these two lines here to actually get an achieved for this question. But yeah, so it's not a bad merit question. Just understanding when you need to square the square to get rid of the square root symbols, and then you should be pretty much good to go. All right, folks. So on to the next question. So what we've got here is a classic question, which is like basically getting rid of the denominator and writing in the most simplest form possible. So all we really have to do is just cross multiply in this case. There's nothing else we can do in this. All right. So we're going to take k plus ki. When I say cross multiply, it is basically just this, which I hate doing this upside down barbecue thing, but reality is it is hey, good to see you, Matt. Yeah, it's a good laugh. Hey, good laugh. Where did I go? Where did I go? Yeah, sorry, got distracted. Okay, so we got k plus ki, and we're going to multiply with 1 plus I, and also in the denominator, we're going to do 1 plus I. But really, we don't really care about the denominator because eventually it's going to be 1 plus I anyway. But you know what? I'll do it both ways, just so that it kind of makes sense. And then we've got 2k over 1 plus I. Now on this side, it's going to get multiplied by 1 minus I and 1 minus I. So all we got to do is, yeah, we just got to cross multiply the bejesus out of it, because, and that's the long thing, right? It's like that's what's going to take such a long time, but it's all right. We kind of have to kind of do that anyway. So in my numerator, I've got k plus ki multiplied by 1 plus I plus 2k times 1 minus I, and the whole thing is now divided by 1 minus I and 1 plus I. So that's pretty much what I meant by the cross multiplication. Then we're going to have to expand all those brackets. So what do we got? We've got k and then ki. This is where you guys got to be a bit careful, right? Because it's so easy to make these mistakes. K and then you've got k times I, which is ki, and then I've got plus ki times 1 and ki times whatever the next thing is. So that's going to be ki again plus ki squared plus, this is a nice simple expansion of the quadratic. We've got 2k times 1, which is 2k, and then 2k times minus I, which is negative 2ki. All of that is divided. Again, we've got to kind of do this. Denominator, we've got to expand it out. So we've got 1 times 1 is 1, 1 times I is I, negative I times 1 is negative I, and then negative I times positive I is negative I squared. Okay, so let's get rid of all the I squareds. So we've got an I squared there, and we've got an I squared there. And at the same time, we're going to try and simplify as much as we can. So we've got k plus 2ki plus, the I squared changes to negative 1. So negative 1 times k is going to be negative k. And we've got plus 2k minus 2ki, and all of that is divided by 1. Plus I minus I is 0, minus I squared is equal to negative 1. Okay, so simplifying this now, let's just see what we need to get rid of. We've got k and negative k disappears, 2ki and negative 2ki disappears, and we are left with just 2k in the numerator, and in the denominator we're left with 2, which means our final answer ends up being just the k there. So grades wise, correct solution gets you a merit. And then correct expansion with common denominator, line 2. What do they mean by correct expansion with common denominator? Okay, so this is probably here that you're looking for and achieved. Yeah, so it's not a bad question, just like lot of opportunities to make like little mistakes here and there. But yeah, that's pretty much a nice little merit question right there. Okay, guys. So question 1E, I'm just going to kind of go through again, just what we needed to do. What we've got here is to re go through this question again. We've got a t there, which we're going to replace those two t's with, and we've got to try and prove it. I'm going to try and write this as small as possible, but we're going to try and work this out. So we've got 1 a minus bi, let's see, that whole thing, right? Stupid thing. We've got a plus bi, and the whole thing squared, divided by 2 times a minus bi and a plus bi. Okay, so the first step we want to do is we are going to actually sort out the numerator. Now, if you look at the numerator, in the numerator, we've got a plus bi in there, right? So that means we've got to have a plus bi here as well. But the thing is, it's going to be squared. So we're going to put that as a plus bi squared and a plus bi squared. So what we've really got here is a plus bi squared divided by a plus bi squared plus a minus bi squared divided by a plus bi squared. So that's the top line right there. Okay, now we've got that divided by, and we're going to put this as, what are we going to put this as? 2 a minus bi and a plus bi. Now notice, guys, I've not actually expanded anything yet. All right, I've kept everything as is. Now the next thing I can do is I can combine this two denominators as 1. So my top part of the fraction is going to look like this: a plus bi squared plus a minus bi squared, and the whole thing is over a plus bi squared. Now this is just the top part of the numerator. Now that's divided by 2 times a minus bi and a plus bi. So that's one thing, right? Now the next thing we can do is, remember this: when you're dividing by something, it is the same thing as saying multiplying by its reciprocal, right? So if I was to do this, I'm going to continue this here so you guys can have a look here. So we've got a plus bi squared plus a minus bi squared divided by a plus bi squared, and that fraction, I'm going to rewrite it like this. All right, I'm going to rewrite it like this: 2 a minus bi over a plus bi. And I think this part is really important, because what we can now do is we can multiply it by the reciprocal of it. So I'm still, as you can see, I'm still not expanding anything. I'm still keeping everything as is. So I've got a plus bi squared plus a minus bi squared over a plus bi squared multiplied by, now flip the fraction over, so I've got a plus bi over 2 times a minus bi. So once I get that, I can get rid of one of my, the a plus bi, I can get rid of it, because that one goes away, and that just ends up being a 1 right there. So what I then have is, in my numerator, I've got a plus bi squared plus a minus bi squared, and the whole thing is divided by a plus bi multiplied by 2a minus bi. So I'm hoping you guys got where I got that from, because if you can kind of see what's happening here, then this question is just going to become a little bit easier. And also, by the way, if you got up to this part right here, I'm actually going to mark this paper as we go as well. If you get up to this part right here, this line, you've done it, that's going to end up being a merit. As for the achieved part is right here. If you get up to here, you actually get achieved straight away for that, getting up to that second line of that question. So now we are going to try and kind of bring this down, because remember, we've got to try and figure out how to go from here to this part here. It's terrible, but right there. That's what we're trying to prove to. So I'm going to start messing around with it a bit more here. Now we can actually start expanding the brackets. All right. So as you guys can see, I didn't expand at all until the very last moment when I can actually get rid of things and make things a little bit more easier. So here I've got a plus bi squared. So that's going to look like this, plus a minus bi times a minus bi, and the whole thing is divided by 2 times a plus bi and a minus bi. Because what you're going to notice now is things are going to start disappearing very quickly, because we've got to expand the quadratic in the top. We're going to get a squared plus abi plus abi plus b squared I squared. Then expand the next bracket. We're going to get a squared minus abi, and then we got minus abi again, plus b squared I squared. Just want to check that if I've done it all right. 2abi, yep, that's all good. And that whole thing is now divided by 2. A plus bi times a minus bi, that's just going to be a squared minus abi plus abi minus b squared I squared. Now I need to go and get rid of all my I squareds. So I've got an I squared there, I've got an I squared there. Putting it together, I've got a squared plus 2abi minus b squared, because I squared is -1, plus a squared minus 2abi, and then we've got minus b squared again, and the whole thing is divided by 2 a squared and then I squared. Oh, we've got another I squared here. So that abi and abi is going to disappear, and we're going to get plus b squared. Okay, now if we look at the top, the numerator, we've got 2a squared, because these two things cancel out, minus 2b squared over 2a squared plus b squared. Take the 2 out as a common factor. We've got a squared minus b squared over 2 times a squared plus b squared. And as you guys can see, we end up with our proof, which is a squared minus b squared and a squared plus b squared. So now if you were to try and expand somewhere in this area, you are going to, you're going to end up getting it very, very messy. But the thing is with these types of questions is that you do not want to expand way too early at all, that you literally just try and keep it together as much as possible until the very end. So yeah, right at the bottom, that ends up with excellence for that question there, for the proof question. Alright guys, so we are going off to question number 2 here. So question number 2, what we've got is, we've got, given that x minus 2 is a factor, we've got to try and find the value of q. So remember that if x minus 2 is a factor, then we can say that f of 2 is equal to 0. So all you got to do is substitute wherever x is equal to 2 and put this whole equation equal to 0 and figure out what q is. So we're going to do that as 2 to the power of 3 plus q, 2 squared minus 17 times 2 minus 10, and all of that is equal to 0. So we've got 18. No, we don't have 18. We've got 16 plus 4q minus 34 minus 10 equals to 0. So we've got 4q plus 16 minus 44 equals to 0. And I cannot believe my head is just hurting at the moment, but And we got 4q minus 28 equals to 0. Rearrange it. So we've got 4q equals to positive 28, and q is equal to 28 over 4, which gives us 7. So, achieved. Question to kind of kick it off with. So yeah, so that's pretty much it for this question. There's nothing really special about this question. Straightforward. Substitute the x value and then figure out what q is. Okay, so going on to the next question. Next question, what we have is find all possible values. All right, nice little clue that they give you guys by saying that it's all possible values, which means we can kind of realize that it's not just going to have one answer. So what we've got here is a modulus is equal to 13. So all we really have to do is we can actually rewrite this as, what can we say? So we can actually say modulus is 13. So we can say 5 squared plus 3k squared equals 13 squared. All right, that's pretty much it. That's what modulus is, right? So we can actually say this is 25 plus 9k squared equals 169, and then rearrange it. So 9k squared is 169, take away 25. 9k squared is 144, and then k squared equals 144 divided by 9. K squared equals 16, and of course, don't forget, guys, you have to put down k is equal to plus or minus 4, because square root of 16 equals plus or minus 4. So that's pretty much what we're looking at for that. And once again, grades wise, we are looking at an achieved. That's basically it for achieved for this question anyway. Okay, so going to question C, which happens to be one of my favorite questions, because this question, I don't know why, it just comes every year. And I have not seen a year where this question has not come, and I'm hoping that the trend continues. Cool. So here we go. What we've got here is we are told that one of the solutions is z is 3 plus I, blah, blah, blah. We've got to try and figure out the other solutions and the value of b. So the first thing I'm going to kind of talk to you guys about here is this. Because it's complex, right? We know that if z is 3 plus I is one solution, then 3 minus I is another solution. All right, so this is just one of those things that you kind of pick up with complex numbers, which means we can actually rewrite this whole equation now. And I guess there's so many ways of doing this. You can actually do this straight in the calculator and figure out what b is. It's a little bit trickier, I guess, for this question. But again, I'll show you guys some of the things. So first thing to realize is we've got a z cubed here. All right, that's the first thing you need to realize. Now, our first solution, which is 3 plus I could rewrite it like this. So I could write z minus 3 plus I. So that's my first kind of like my bracket. Because you know, when you have a cubic, you're going to have like 3 brackets. That's my first bracket. My second bracket is going to be z minus 3 minus I. And then finally, my third bracket is going to be, I'm going to call it AZ plus B. All right, these are the 3 brackets. Maybe I shouldn't use B. Hang on. Let's try something else. What's another letter I can work with? P and Q. Let's go with P and Q because we got a B in there and I don't want to kind of mess it up. So once we get that, what we do know is we know that Z multiplied by Z multiplied by PZ is going to equal to 2Z cubed. All right, so that's the first thing we're going to do. Z times PZ equals 2Z cubed. So here on this side, we've got PZ cubed equals 2Z cubed. So we can say P is equal to 2. So in other words, I figured out my first part of this bracket, which is 2Z. Then my second thing is to try and figure out that value of q. Now to do that, I've got negative 3 plus I multiplied by negative 3 minus I multiplied by positive q, which all equals to minus 30. Yep, Tim, you can actually do that. That is a completely fine, that's one way you could do it as well. That's not a problem. As I said, there's like quite a few ways you can do this. So if you guys have a look at some of my previous exam questions, I would have done it slightly differently as well. So have a look through that as well if you can. So here I've got negative 3 plus I multiplied by negative 3 minus I multiplied by q equals to minus 30. So the two negatives disappear. I've got 3 times 3, which is 9. I'm just going to leave that q out there for now. And I'm going to do this part here first. So I've got 9 minus 3i plus 3i. It's not going to matter. And I've got minus I squared. Q equals minus 30. Now I squared is equal to negative 1. So I'm going to get 10q equals negative 30. And q is equal to negative 3. So my final factor that I have is 2z minus 3. Cool. So if we have a look at this, just going to kind of put them all together now. And I think I've actually made this a bit longer for you guys, but that's all right. So we found our final factor, which is 2z minus 3, which means we also found our final solution, because our solutions are going to be 3 plus I, 3 minus I, and when you've got 2z minus 3, rearrange that, you're going to get z is equal to 3 over 2. So 3 over 2. So these are our three solutions. But we still need to figure out what the value of b is. And that's right there. So as Tim was kind of mentioning it, so we could actually substitute 3 plus I. And for this, I am going to use the graphics calculator to kind of show you guys how to do this as well. So what I'm going to do is I'm going to substitute z, 3 plus I as z. So I'm going to get 2, 3 plus I to the power of 3 minus 15 times 3 plus I squared plus b times 3 plus I minus 30 is equal to 0. So what I'm going to do is I'm only going to do this part in the calculator, guys. So this part and this part in the calculator. All right, now if you are a bit brave and you want to use the solver function in your calculator, you could actually do that as well. But yeah, I mean, we can kind of do it multiple ways, but I'll show you guys this method first. Okay, so what I'm going to do is I'm going to use the answer function as a bit of a shortcut here. So I'm going to put down 3 plus, my I button is under here, shift 0, that's my 3 plus I. Cool, I've got that. So right now, anytime I click on answer, it's going to lock in as 3 plus I. So what I'm going to do is I'm going to go 2 multiplied by answer to the power of 3 minus, what do we got, 15 is it? Yep, 15 times answer squared, and then minus 30. So what this gives me is negative 114 minus 38i. So all I've done is I've calculated whatever this yellow part here is. The yellow part is equal to minus 114 minus 38i plus b times 3 plus I is equal to 0. So I'm going to rearrange it. So I've got b 3 plus I equals 114 plus 38i, and then b is equal to 114 plus 38i divided by 3 plus I. So for that, I'm just going to be a bit lazy and just use the calculator here. So that divided by 3 plus I. Just checking the answers, guys. Yep, so B is equal to 38. So grades wise, we're looking at other two solutions found and B found. So you need this and you need these two things to get a merit. For an achieved is finding this, I'm going to put this, or one of this for an achieved. Bit of an annoyingly long question, but it is what it is. Yeah, so it's a good point there, rotation, if that's what you meant by. But yeah, I was just saying that like you could potentially put any one of these three solutions in here, put it equal to 0, and actually figure it out. So we didn't need to put the 3 plus I. We could have also done the 1.5 and actually try and solve that as well. Okay, so we're going to go on to the next question, guys. Cool. So with question D, it is a bit of an annoying question, as I said before. Now, the long method can actually be quite tedious, where you're going to have to like put u over v, right? Like you're trying to find the argument of u over v. So you got u over v equals p plus pi divided by negative q plus qi. And I can tell you this right now, this is going to be like a total pain to try and rationalize the denominator. But remember this, when you have argument of u over v, and I'm talking about this is one of the rules you guys will have learnt. This is the same thing as saying argument of u minus argument of v. All right, so it is pretty much that's the hint right there. Like this method here, I'm going to put this. If you were to put go with the green box and kind of like go in that direction, you're going to end up wasting about a good 5, 6, 7 minutes. All right, while the yellow method here, you're probably going to be done with this question in about 2 minutes. Why? Let's have a look at this. U is equal to P plus PI. P plus PI. Okay, so I'm going to draw the P plus PI first. So that's P there, and that's P. Yes, we are good to go. It's working again. Which means the angle we're looking at is 45 degrees. So argument of U is 45 degrees. Then we've got V equals negative Q plus QI. That is negative Q is here, positive Q is there, which gives us an angle of 135 degrees. So argument of V is 135 degrees. And if we look at this formula here, we can say that argument of U over V equals 45 degrees minus 135, which gives us negative 90 degrees. So yeah, we pretty much got to get this answer right for a merit. You can get achieved if you were to go through this and kind of like rationalize and then kind of solve it, then you can get a merit. But there's nothing wrong in doing the method that I've shown here, which just gets you a merit straight away. All right, folks, let's get to the final question, which is question 2E. Well, when I say final in this part anyway. Now, what you guys have got here is classic Cartesian plane question, all right? So all you got to do is, and I know that in Victor, you've been asking about the whole line thing. This is pretty much, this is what it comes down to, that whole line thing is we're looking at the modulus, all right? So the first step in this question that we're going to do is we're going to put down z is x plus iy. All right, we're just going to put that down. That's anytime you're doing like a Cartesian equation question, locus question, you just put this straight up. Don't even worry about it. Just put x plus iy. And then what you got to do is get rid of the z. So if you think about it, we've got a z here, and we're going to replace it with x plus iy. So we got x plus iy plus I squared plus, what have we got here? Z minus I. So we've got x plus iy minus I squared equals 10. So because, well, where did it go? Because we know that modulus, like I'm just looking at the modulus, right? And I guess I need to be a bit more specific with this. This part right here, the modulus, I know that the modulus is square root of whatever the real part is. Real part in this case is x squared. The imaginary part is y plus 1 squared. All right, now I'm going to try and kind of explain how I got that real quickly. So the first thing I'm going to do is I'm going to put this as x plus y plus 1i, and it's still a modulus squared, plus x plus y minus 1i squared equals to 10. Now, because it's modulus and then squared, I can forget about the square root, because the square root squared is just, it's going to get rid of itself. But I'll show you guys anyway what it looks like. So this is going to look like this. Square root of x squared plus y plus 1 squared. That whole thing is the modulus, but we still got that square to deal with, plus square root of x plus y minus 1, sorry, x squared plus y minus 1 squared. That whole is also getting squared, is equal to 10. Now, because square root and squared, they're next to each other, we can get rid of them. And what we're going to end up with is x squared plus y plus 1 squared plus x squared plus y minus 1 squared equals to 10. Now, as you guys can see, the only thing we really need to do here is pretty much just expand and simplify, and that's it. And once again, my computer screen is frozen. Nope, it's not frozen. That's good to know. Cool. So once we got this, we need to expand the y plus 1 squared and y minus 1 squared. So we're going to get x squared plus y squared plus 2y plus 1 plus x squared plus y squared minus 2y plus 1 equals to 10. So putting everything together, we're going to get 2x squared plus 2y squared plus 2 equals to 10. We've got 2x squared plus 2y squared equals 10 minus 2, which is 8. Get rid of the 2, as it's a common factor, equals 8. X squared plus y squared equals 8 over 2, and x squared plus y squared equals positive 4. So pretty much that's all that you need for this particular question. All right, so excellence wise, you're going to get the final line gets you an excellence. Correct expanded expression line 4. So it's 1, 2, 3, 4 gets you a merit. So merit is this line right here. Get up to there and you end up getting a merit. But I don't think there is no achieved for this question. So it is just a straightforward M or a E question. So Cartesian plane, like locus questions, always remember, put z equals x plus iy, get rid of the z, and then just expand and rearrange and bring things together, and you should be good to go for a nice and straightforward excellence there. All right, guys, so on to question 3. What we've got here is nice achieved question. U, V in polar form. So all we've got to do is, what do we've got? We've got 12k cubed, because remember that we can rewrite this like this: 12k cubed over 2k cis of pi, take away pi over 3. All right, this is just some De Moivre's theorem that just have to keep in mind. Once you do that, it's just 12 over 2 is 6, k cubed over k is k squared, cis pi take away pi over 3 is 2 pi over 3. How do I get that real quickly? Well, I know that pi could be written as 3 pi over 3. 3 pi minus pi is just 2 pi, and then we're good to go. Grades wise, achieved. Okay, so going to question 3b. Once again, we are coming back to this z squared thing again, well, modulus. So we've got to actually work out what modulus of z is first. So modulus of z is going to be square root of 5 squared plus negative 1 squared. And then modulus of w is going to be square root of negative 2 squared plus 3 squared. So in this case, we've got square root of, what do we got? Square root of 25 plus 1, which is 26. And then on this side, we've got square root of 4. 4 plus 9 is 13. So as you guys can see, modulus of z squared, that's going to be square root of 26 squared equals to 2w squared, which is going to be 2 times square root of 13 squared. And you can kind of straight away see that this is going to work out real nicely. 26 is equal to 2 times 13. Yeah, so that's pretty much it. So you don't really need to do much apart from just kind of show that both of these things equal to each other. So 26 equal to 26, you're done. Ends up with an achieved for this question. All right, so question 1C. What we've got here is one of these little proof questions again. All right, so we've got a plus bi. Conjugate. So if z equals a plus bi, then z conjugate is a minus bi. So we're just going to show that this is a real number, right? So we're going to go a plus bi multiplied by a minus bi over a plus bi plus a minus bi. So as you guys can see, all I've really done is just substituted z and conjugate of z, that's all. So in the numerator, what we've got is expand out the quadratic. So we've got a squared minus abi plus abi and minus b squared I squared divided by bi disappears, so we've got a plus a, which equals to 2a. In the numerator, these two things disappear, and we've got I squared is equal to -1, so we're going to get a squared plus b squared over 2a. And you can kind of say this, well, this is real. You don't really, there's no I, so this is a real number, and that's pretty much it. Correct solution with a statement indicating real part or imaginary part equals to 0 gets your merit. So you do need to kind of mention some sort of reason to get merit. Both numerator and denominator evaluated correctly. So just getting up to here is going to get you an achieve, but giving the reason is going to get you a merit. Cool, so that's basically it for question C. Yep, sorry, that was a little mistake there. That should have been 2A. All right, moving on to question D. Possibly one of my favorite questions with question D is when we're doing complex roots. So with complex roots, I know I've done some couple of tutorials before where you just kind of, how do I say it? There's this algorithm, right? You basically take the complex number, convert it into polar form, and then you literally just add how many other angles that you need to go with. So let me show you guys what I mean by. So when we have z to the power of 4, we know that there's going to be 4 answers, and the difference between each of those 4 answers is 90 degrees. All right, so if you find one root, then you just got to add 90 degrees to all of them, and you're pretty much good to go. So the first thing is looking at Z4, right? And putting it into a polar form. So I'm going to kind of draw this out here. Negative 16K8 is somewhere here. All right, that much I know, negative 16K8. Now the angle that it's going is going to be 180 degrees. So that is what I'm going to start with. So Z4 equals, now because it's modulus, it's going to be real number, so it's going to be 16k to the power of 8 cis 180 degrees. Now looking at my first root, I can say that z is equal to 16k to the power of 8 cis 180 degrees to the power of a quarter. So z is equal to 16k8 to the power of a quarter cis 180 times a quarter. So from here, I can see that my first root, 16 to the power of a quarter is 2. K8 to the power of a quarter is just k squared. Cis 180 times a quarter is 45 degrees. So this is my first root, and because this is my first root, and I gotta just add 90 degrees to all of them, I'm just gonna do this. Just write this all down first. 2k squared cis of everything. 45 plus 90 is 135. 135 plus 90 is 225. 225 plus 90 is 315. Now you can actually write these answers in degrees. So I know some people actually end up working in pi and kind of gets a bit messy, but trust me, you can actually do this in degrees. I'm looking at the answer schedule right now. It does say accept equivalence in degrees. So grades wise, these 4 answers is going to get you a straightforward merit. Achieved is Z4 written correctly in polar form. So that's achieved here, or you could get achieved there as well for the first root. Or if you get all the angles correct, you could get an achieved as well. I would strongly recommend you guys to have a look at one of my tutorials from last year, I think, complex roots tutorial. It pretty much goes through this. I think I dedicated like one whole session on this, and it's pretty straightforward once you get the hang of it, because it is a nice little easy merit question to kind of keep in the back of your hand. Cool, that's basically it for this question, guys. All right, guys, so we're going to the last question, which is a bit of a long one, so I do apologize. It will take a bit of time to kind of get through this question. It is a 2-part question, so we kind of have to mess around with it quite a bit. So to start off first, we've got 2 complex numbers, u and v. We're going to put down u is equal to a plus bi and v as c plus di, okay, because they're 2 completely different complex numbers. So the first step that we've got to do is we've actually got to prove this part here first. That's the first thing that we've got to do. Once we prove that, then we've got to do u over v is purely imaginary. So I guess we're going to try and do one part at a time. So the first part I'm going to do is the modulus of u plus v. So modulus of u plus v is going to be a plus bi plus c plus di and the modulus of that. So if I look at it like this, I've got a plus c and then b plus di. And if I put this as a modulus, I'm going to get a plus c squared equals to, not equals, sorry, plus b plus d squared. All right, so that's the first kind of idea behind the modulus of u plus v. The next thing I'm going to do is u minus v. So doing u minus v, I'm going to do the same thing. I've got a plus bi minus c plus di, like this. And when I expand that little bracket out, I'm going to get a plus bi minus c minus di, and then collect all the real values, plus b minus di. And then modulus of this is going to be a minus c squared plus b minus d squared. Now it does say that both of these modulus are actually equal. And that means I could say that basically these 2 things are equal. Get rid of the square root symbol, and I've got a plus c squared plus b plus d squared is equal to a minus c squared plus b minus d squared. So that is what I have got so far. All right. Now I need to expand these little brackets and kind of like bring it down to like a nice little statement. So it's a whole lot of quadratic expansions, but that's what it is. So I got a plus c times a plus c. That's going to give me a squared plus 2ac plus c squared. b plus d squared is going to give me b squared plus 2bd plus d squared. And then on the right hand side, I've got a squared minus 2ac plus c squared plus b squared minus 2bd plus d squared. Hoping you're with me so far. Then we need to get rid of all the things that we don't really want to deal with. So a squared and a squared disappear, b squared disappears, d squared disappears. Yep, all of that gone. What we're left with is just 2ac plus 2bd equals negative 2ac minus 2bd. So what do we have next? We can rearrange them, which means we're going to get 2ac plus 2ac plus 2bd plus 2bd equals to 0. We've got 4ac plus 4bd equals to 0. Now we can get rid of the 4, and what we simply have is ac plus bd equals to 0. So this is pretty much that first part of the proof that we worked out. So we basically did this. If u plus v equals to this, then what we end up with is ac plus bd is equal to 0. Now we need to use this information to try and prove that u over v is purely imaginary. So we're going to do u over v here, which is a plus bi divided by c plus di. So the first thing we've got to do is we've got to rationalize this denominator. So we're going to multiply it by c minus di, and the numerator also by c minus di. So when we do this, in the numerator we've got a plus bi multiplied by c minus di. In the denominator, because it's difference of two squares, I can rewrite this as c squared minus d squared I squared. Expand the numerator. A times c is ac minus ADI plus CBI minus BDI squared. Well, that's a whole lot to take on, but we're there. And then in the denominator, we've got c squared. I squared is equal to negative 1. So negative 1 times d squared is positive d squared. And so in the new, we've also got another I squared, which I forgot about, but that's okay. Minus ADI plus CBI, and then here I'm going to get rid of the I squared that's here, which becomes negative 1. Negative 1 times negative BD is positive BD over C squared plus D squared. Now, I can split this up into real and imaginary. So I've got AC plus BD over C squared plus D squared. And then I've got plus minus ADI plus CBI over C squared plus D squared. And as you guys can see, we actually showed that AC plus BD is equal to 0. And because it's equal to 0, we're going to get 0 plus negative AD plus CB, and that's with the I on the outside, over C squared plus D squared. And at this point, you can actually say, therefore, U over V is purely imaginary. That's pretty much what you need to do for this particular question. Actually, it didn't take that long as I thought. It was just that first part, that yellow part that I highlighted, that you've got to kind of come up to some sort of statement, like the statement here. Once you have the statement, then it's just learning when to substitute it to get rid of the real part. Again, these types of questions, it actually does work out quite nicely, these proof questions. It is something to keep in mind. Grades wise, we are looking at obviously final proof, which is excellence. Correctly simplified expression for u plus v and u minus v gets you a merit, which is somewhere here. And then correct expression for that gets you an achieve line beginning with arrow. So you're looking at achieve just getting up to this part right here. Yeah, so this question, I think it just has like a lot of expanding, as you mentioned, rotation. It does have a lot of expanding and rearranging, but that is what complex numbers in algebra is. Any feedback on this new format is appreciated. As I said, it was the first time I tried to do this with a live stream and then try to edit the video out later. Hey guys, that is basically it for this video. As always, don't forget to like this video, share this video, and of course, subscribe to keep up with the latest content. There should be some playlists popping up. Check them out. Good revision material. And as always, thank you for watching.